Well, good afternoon, everyone, and good day to wherever you happen to be in the world. Today, this is one in a series of IEAGHG webinars. It is, in fact, the fourth webinar we've done on CO2 DataShare. My name is James Craig. I'm the Technical Program Manager for IEAGHG. And today, we're going to look at how CO2 DataShare can be used to model the Sleipner benchmark work. The next slide, please. So for those of you not familiar with IEAGHG, we are a technology collaboration program founded in 1991, supported by 36 members in 15 countries, plus OPEC, EC, and the CIAB. We set strategic direction, specifically on greenhouse gas control. We're independent, but we're not advocates. So next slide, please. So fundamentally, we underpin commission R&D on greenhouse gas mitigation options. We track capture technology development and costs, and we monitor geological storage of CO2 and provide our members with independent technical input. Next slide, please. Our members, as you can see here, combination of countries and industrial players with a serious interest in CCS. Next slide, please. So CO2 DataShare is a digital laboratory. For those of you who maybe are not familiar with it, it was set up with funding from the US Department of Energy and the Norwegian government. And its vision is really to accelerate deployment of CCS by allowing researchers to use best available data to enhance the knowledge of, in this case, CO2 storage, and to build capacity, by which we mean expand that knowledge to other people researching in this field. And the goals are to promote international sharing of reference data, which in this case is the Sleipner dataset, and thereby build a network of international stakeholders, data users, and public agencies with a direct interest in CO2 storage. And with that, supporting spin-off research and innovation by using these data sets and by using generating, hopefully in the future, new data sets. Next slide, please. So today, what we're going to do, we have 5 brief presentations from researchers based in Norway who have been working on the Sleipner dataset, which is the dataset that CO2 DataShare holds. The first of these will be from Sarah Gazda from Norse. The second will be from Odd Anderson from Sintef. And the third will be Tor Ingvald Bjornaro. Apologies for that appalling pronunciation. And then you'll notice, if you have specific questions about these presentations, please pop them into the chat box, and we'll have a very brief intermission for specific questions. Next slide, please. And then we'll have another 2 presentations. One from Tor Sandberg from Norse, and then we will conclude from Adil Zahid from Equinor. Again, if you have specific questions about those 2 presentations, there will be an opportunity to address them. And then Philip Ringrose from Equinor will give an overview of the 5 and what we can deduce from them. And then we'll have an open session where we will present questions which you can submit via the chat box. Before we move to the first presenter, you can submit questions via the chat function, and we'll use these to address the particular queries that you have. We will be storing and posting this webinar on YouTube shortly. And if you do have further questions that we're not able to answer, we'll do our best to address them, so please send them in. But obviously we won't necessarily be able to do that immediately. So I'd like to now ask Sarah to begin with the first presentation, and I will switch off. Oh,
you want to say something, James? Go ahead.
I forgot to mention, please remember, highly pertinent, GHGT 15 is next month. We are open. It is a virtual conference, obviously, but it's a very reasonable price, and we will be covering the full span of CCS. There will be panel discussions, live panel discussions, and plenaries. So I would welcome and I would urge you all to book if you haven't done so already. So if you could, we'll now move to Sarah.
Good, thanks, James, and thanks to IEAGHG for organizing this. I'm very excited actually to hear all of the panelists' talks, because we've been all working on these on this data independently, although some of us are direct colleagues or close collaborators. So it'd be very interesting to me to see how we've what we've taken away. So I'm excited. I'd just like to acknowledge my colleague Sven Tveit, who worked with me on this project, and this was funded by Gassnova as a feasibility study. So go to the next slide, please. So the study that we applied for, that was supported by Gassnova, was to look at history matching of the plume using a simplified approach. And the idea here was to increase efficiency in the history matching routine. And we were going to test out a couple of different approaches. So although we are performing history matching, I will definitely caution that these are preliminary results, what we managed to get out of this was really a lot of lessons and learnings that we can take forward in further developing this approach. Next slide, please. So this was the overall workflow, and this is a very standard workflow for history matching, where you start with the parameter distributions, you have a forward simulator, you put these into your, in this case, we've picked an ensemble-based history matching workflow, and in the end, we end up with a matched model. And underneath, I show you the areas where we've attempted to introduce some types of efficiency, forms of efficiency, that can get us to a decent match model in the end. And the first is really looked at the parameter distributions themselves and using past experience to select which parameters we would focus on and what kind of distributions we would have. So that would narrow and constrain what would be sampled in the workflow. And the second aspect is about the forward simulator itself. And here we introduce a simplified model that helps reduce complexity and then achieve efficiency in reaching the objectives of the study. The third is a selection of the actual history matching tool, and here we've chosen a robust framework that's applied routinely in reservoir simulation. So in the end, we hope we end up with an efficiently obtained but sufficiently accurate matched model. Next slide, please. But what we also think about in the back of our minds is really using this first pass, using a simplified approach where you take some initial parameters, a reduced model, and have an initial matched model that then you could move towards a full complexity history matching, where you now have constrained parameter distributions, but use a full physics forward simulator to end up within the same type of workflow to end up with the final matched model. You can think of this in a hierarchy workflows, and you can even introduce a further simplification in one step above So in mix and match, depending on the problem that you have. Next slide, please. So the first aspect is about the parameter selection, and for the Sleipner CCS or CO2 storage project, there's been, of course, a lot of experience gained over the past 25 years. So we use this knowledge to increase efficiency through intelligent selection of the parameters we're going to focus on. And the three are the feeder permeability, convective dissolution, and temperature as opposed to composition. So up on the top right, I show you the feeder properties, and the feeders have been previously called chimneys. A variety of different names have been used in the past, and it's very well known that these, of course, are essential for how CO2 is migrating both laterally and vertically within the Sleipner sand. On the bottom left is the temperature gradient. There, of course, have been many studies about the temperature and the uncertainty of the temperature, and then pointing to a study here where we looked at comparing uncertainty of temperature versus uncertainty of the plume composition in the CO2 injected fluid having some impurities, and landed upon that temperature really is the main factor, and so we chose to focus on temperature. And on the far right bottom is convective dissolution. There's been a wealth of studies on convective dissolution from a theoretical standpoint, modeling, laboratory, and there's been one time directly applied to the Sleipner. We're looking at the layer 9, and I'll just make sure to point out that a lot of our experience is based on the top layer, and we haven't looked at this for the full Sleipner model, and that's where we move today. Next slide, please. So the forward model, and here I don't have nearly any time to go into any details, we selected a so-called vertical equilibrium model called VESA. That's an in-house tool we have here at Norse, but it is also very well-studied approach to gravity-dominated CO2 injection. And here the idea is you collapse a 3D system into an equivalent 2D system, and what you're essentially modeling is evolution of CO2 thickness. And over the years, this type of approach has been expanded to include things like convective-driven CO2 dissolution through an equivalent, again, not resolving the fingers, but upscaled version of that process, and also looked at different ways of handling vertical fluid migration. The model that we have has a PBT based on Spahn and Wagner and viscosity model, so it is a CO2 properties, it is a full model. And we have a Python-based interface that we've coupled now to the history match workflow. Move on to the next slide. So to make the Sleipner model into something appropriate for the forward model that we've chosen, we need to transform the 3D system into a 2D system. And here, because of this layered aspect, the 9 layers, we've taken each of these units and separated them out and transformed them into a stack of 9 two-dimensional units. So it's basically just extracting the top surfaces and doing some very simple averaging of the properties in depth, and nothing too controversial about that. The thing that's the trickier part here is the vertical flow between the layers. The VE model, the VE modeling approach assumes horizontal flow, so you have to have a vertical transfer between the 9 units, and this we handle by source sink terms across the shale units. So the shales are implicitly there in the model dimensions, but the flow and saturation don't explicitly show up in the simulation grid. And so the real advantage here is the obvious one, is that you reduce the number of grid cells of this model from 2 million by compressing each of these 9 layers into a single 2D surface to about 70,000 cells. So already we gain an enormous amount of efficiency just from that step. Next slide, please. Just a quick comment on the history matching. Again, what I've said is we've chosen a well-established framework called ensemble-based methods. The particular variant is ESMDA. This is not my area. I point to the ensemble smoother with multiple data simulation. Those of you who are into data simulation know what I'm talking about. But the point is that it is a very low computational cost way of getting the uncertainty estimates for the quantities of interest. You can run things in parallel in terms of the samples run on the forward simulator. And again, this also has an in-house Python toolkit that we've developed here at Norse with a wide variety of methods, of which VESA is one of them. Next slide, please. Okay, so combining DESA with this ensemble-based method, we have to make a couple of decisions. And this, again, is the feasibility study of what the decisions are and what they lead to. So first is what we compare. What we've decided is to compare the Plume outlines via what's called the sign distance function that drives the updating in the iterations. And this is essentially the distance from the thickness, so the Plume thickness, which is what the VE simulator gives you, the contour at 1 meter, compared to the seismic, the polygons derived from the seismic. We don't add in any other uncertainty in the actual observed data. We take the observed data as true. The other second thing is about the permeability of the feeders. We've set in a requirement that the permeability of the feeders cannot exceed the permeability of the formation units. This is to do two things. First, it has to preserve the VE assumption, which is we can get into that another time, but also the geological realism. The feeders, of course, are more than likely some kind of sand injectites or various things, and they can't have a permeability higher than the sand from which they've originated. It would be very difficult to imagine a way that would happen. But so what we do is when the ensemble-based code wants to push the permeability of the feeder, we just expand the area. So we're eventually matching the transmissibility of the feeders. And then, of course, we have reservoir temperature, which is a very standard, easy thing to do, and the dynamic dissolution rate of CO2 in brine, this pulling CO2 out of the plume into the water column below, and that also is a parameter that's matched. Next slide, please. So just to give you a flavor, these are the results without any history matching. I think we put in the prior, in this Bayesian framework, you have to suggest a prior distribution. So I think we put this in. And you can see the layers 1, 2, 3, up to 9. The layer 9, of course, is the one that's most well studied. And what you see very clearly is that this main feeder, so there are 3, if I recall correctly, 3 feeders, one which shoots up the entire, through the entire formation. And this is really acting as a pipe. If you don't do anything else, it just shuttles CO2 directly to the top, and you don't get any CO2 spilling into these other permeable formations. What we also see here is that topography really plays a role. And if you go to the next slide, I'll show you a quick highlight of that, where you're already learning a little bit about this model that, and compared to the seismic data, on the left is an example of is the simulation we just saw, compared to the white, which is the seismic polygons. And there are discrepancies, obviously, because maybe we haven't matched, but I think they're also very driven by the topography, which is shown on the right, which is the depth of the top surface. And it's going to be very hard to match the seismic polygons with the topography that we have, because as you see where the arrows are pointing, the seismic polygon is landing basically on a low, and CO2 is collecting in the blue, which is the high regions. So it is what it is, but it's just something to keep in mind as we move through. Next slide, please. And this is showing the same for layer 5, where you have a discrepancy, sort of a region, a blue region that's pulling CO2 away from what would be where the seismic is saying it should be collecting. So these are things we have to think about. Next slide, please. So this is the optimization by history matching, and what we chose to do, again, we made some choices to help speed up the process, and what we learned from this was that we chose to optimize the match in layers 5 and 9, and the reason we did that is because most of the CO2 is accumulating there, and also you have the shadowing effect. There's more uncertainty in the lower layers, so we focused on those, and what we find is that we're getting a better match than if we don't do anything, but it is still very difficult to get to match to these polygons. And there's very little change in the other layers, but that's to be expected because we haven't tried to match those. And what you see is that a lot of the CO2 is still collecting in the first layer, and that's not what you want, but it's very hard given another way of trying to match the data with other types of uncertainty to get that to evolve. Next slide, please. I think I'll skip the next one. Go ahead, Tom. Yeah, so there's the distributions of the feeder permeabilities, and the main feeder is in 1, 2, is in the first, it's highlighted there in red, and if you click one time, Tom, what we're seeing is the development of the distributions from the prior, which is shown on the very left, to the individual posterior distributions. The dotted line is the maximum permeability of the feeders, and you can see some of the feeders are pushing up against that maximum, but then that's where we're expanding the feeder area. Next slide, or next animation, I guess. And then what we see is that it's pushing the permeability of the feeders, where it's trying to keep the CO2. The history matching routine is trying to keep the CO2 into the layers where it's wanting to collect, and that's mainly in 5 and 6, where it's trying to keep that CO2 in 5 to accumulate CO2 there to match the polygons, and then pushing it up elsewhere to get the CO2 to move up. Next. And then these are the ones where I have still a lot of uncertainty in terms of the permeability of the feeders, the main feeder, and it's trying to get again more CO2 into the regions where it's expecting to have more accumulation. Next slide. And just to say, the other two feeders, the southwest and northeast, the uncertainty is still too high to say whether or not we've landed on anything there. As far as convective dissolution, really quickly, and temperature, or I should say the temperature gradient, there we see again from the movement from the prior to the posterior, obviously there is having an effect here of how the routine is pushing the parameter value up into, for example, higher dissolution due to convection and higher temperature gradient, which means a higher, greater temperature at the top surface, and that of course affects density. So it's which of course then it affects the plume volume. And these are all within the ranges that we're expecting, but we did of course give the constraints at the beginning. But the overall quality of the history matching, it does improve dramatically, but it is not perfect, and that is a good thing to take forward. Next. Yeah, just to say very quickly about simulation time. So the main advantage, of course, of this was that the sequential forward model only takes a few minutes on a desktop computer, and the entire routine took, with 60 members and 4 iterations, less than 3 hours on our local cluster here. Next slide. So finally, a lot of lessons learned, but it again emphasized this was a feasibility study about incorporating a simplified model into a history matching framework that I think was successful. The selective matching was mixed success, and there's still a lot of uncertainty that hasn't been resolved yet. And I think, you know, we were trying to get the efficiency maybe too good, and we suddenly have a lot of room to exploit more, you know, matching to more layers and also to more times. We only match to the final time. Further studies, we could think about combining what we're matching, so focus on area in combination with the outline approach. And also we should probably investigate this cross-shale vertical flow, those parameters that are there, if they could either be matched or be understood a little bit better how they're affecting. But the general learnings, I think, for CO2 storage history matching is that, especially in situations like Sleipner, where you are closer to the critical point, temperature really makes a big impact. And also convective dissolution, with or without the critical point, really does have an impact on the matching. So, and also, as I pointed out, that when gravity is dominant, and as it is many times for CO2 storage, it's really important that either we have to update the topography model or take more precautions when building the topography model. That will definitely greatly facilitate this history matching. So I think we've demonstrated that we can use simplified forward models, and it really gives us some new opportunities to explore a much wider parameter space. So at that, I think I will close.
Right, thanks, Sarah. We'll move straight on to Odd.
Hello, can you hear me? Hello?
Yes, I can hear you. I assume everybody else can, so please proceed.
Good. Next slide, please. So the goal of this study was to take the new Sleipner benchmark model and use it to simulate the CO2 storage operation between 1996 and 2010. We further seek to calibrate the model by tuning key parameters to obtain a better match with the actual observed data of plume development. And we also benefit from this work to further the modeling capabilities of MRST, which is our in-house open source software, to handle these tasks. Next slide, please. So Sarah has already talked a bit about the model. I'll mention the things that were important for our study. The Sleipner benchmark model contains several different types of information of importance to our study. There is the simulation grid itself, of course, and you note that the architecture of the reservoir is such that we have 9 layers of high permeability sandstone separated by thin horizontal layers of low permeability shale. Other important pieces of information are the location of the chimneys, where CO2 is assumed to easily migrate between layers, as Sarah was talking about. Also, the assumed rock properties. The well information of a particular importance was the injection well position and the annual injection rates, and the observed CO2 plume outlines for each layer as measured in 2010. Next slide, please. So a word on the methodology. We seek to calibrate the parameters that are mentioned here, which is the density rho of average density of CO2, porosity of the sandstone, and permeability of each layer of sandstone and of these chimneys. So we depart from the information that is provided by the benchmark model, and we run a numerical simulation of the injection operation between 1996 and 2010. Next view, please. We use the CO2 lab module of MRST for this forward simulation. Next view, please. So we get the result from the simulation. Next view. And our optimization engine compares the outline of the CO2 plume as obtained from the simulation with those that have been observed from the seismic and assesses degree of fit. Next view, please. Based on the gradient of the result with respect to the calibration parameters, the optimization routine proposes updates to these parameters. And we run a new simulation with updated values, which leads to another result. And we keep iterating like this until no further improvement can be made by adjusting the calibration parameters. One thing to note here is that we will need to run many simulations for this framework to work. And a full 3D simulation of the Smeaheia dataset on the standard computer that we use takes about 9 hours. Next slide, please. So for this computational reason, we resorted to a similar approach as Sarah was talking about, namely the use of vertical equilibrium modeling. If you look at the left, you see a cross-section of a typical simulation of injected CO2 migration upwards in an aquifer. And as you can observe, the CO2 tends to collect on the top and the water on the bottom. If we can assume this to always be the case, which is reasonable at Sleipner, as supported by many previous studies, we can drastically reduce the computational requirements of the simulation problem by considering full vertical columns rather than 3D cells. In practice, we reduce the model from 3 to 2 dimensions with a dramatic reduction in simulation time for results of similar quality. However, in the Sleipner model here with layers, we do have vertical flow between the layers, and we do not have vertical equilibrium throughout the reservoir, but only in each layer. Next slide, please. So we have developed a hybrid grid, a hybrid model at SINTEF, which allows us to use simulations where we use vertical equilibrium in each layer separately, coupled with standard 3D simulation in regions with significant vertical flow, like the chimneys. On this figure, you can see that each sandstone layer is described by pillars rather than stacks of 3D cells, and one pillar is highlighted in red. Whereas the chimney toward the left consists of fully resolved 3D cells. So there are 3 chimneys, but we only see one on this particular slice. And this approach allows us to run the whole simulation in 4 minutes, compared to the 9 hours that I mentioned for 3D. Next slide, please. Just a quick word on the criteria used for matching the plumes. In order to compare the simulated and observed plume, we compare the height of the simulated plume with the observed outline. And we penalize regions outside of the observed outline, where the height of the simulated plume is higher than a given threshold. And we also penalize regions inside the observed plume, where the height of the simulated plume is lower than this threshold. And this threshold is supposed to be comparable to the seismic resolution. So I'll now talk about the results. Next slide, please. First, we here see the observed plume outlines in red, superposed on the simulated plume in yellow for each layer, with layer 9 being the top one, bottom right on this figure. As you can see, the unoptimized results lead to a rather poor match. Next slide, please. After the optimization, here we have only optimized with respect to the Plume outline in layer 9, and we get the following result. So the improvement is modest at best. So what is going on? Next slide. And this is similar to what Sarah was talking about. Since CO2 will need to migrate upwards, the topography of the top surface is very important in determining the actual shape of the plume. This is similar to how the shape of a lake is very much determined by the topography of the terrain. So by comparing the top surface of the model with the observed outline, we conclude that these are not really compatible. We have these ridges in the geometry of the grid that cut through the observed outline. And we conclude here that a good shape match is not actually possible without actually modifying the top surface. Next slide. Next, yeah. So to test this, we replaced the top surface of this model with the top surface of a previously released benchmark model of Sleipner by Equinor. And this previous model has been shown to lead to a better fit in previous studies. So if we now run an optimization using only the topmost layer as target for comparison, we get the following result. And we observe that the match in layer 9 is significantly better, although not perfect. Next slide, please. If we try to optimize for all the layers, not just the topmost one, we observe that we get improved matches in some of the lower layers, but at the expense of the match in the top layer. Next slide, please. So all these plots show that the we see here are the relative adjustments of parameters, where one refers to the baseline value. The left column shows the adjusted permeabilities for each of the 9 sandstone layers. The middle column shows the adjusted permeabilities for the chimneys, where the main big chimney is the one on the left. And the right column shows the adjustment of density of CO2 and the porosity of sandstone throughout the model. And each row corresponds to a particular optimization, as mentioned in the bullet points on the right. One question one may ask when we see these adjustments is, how much trust should we put in these factors? A numerical model like this has many sources of errors. We have the parameters, of course, but we have also the model geometry, the overall architecture, heterogeneity, discretization errors. There are all sorts of model simplifications and assumptions that may be better or worse. We have errors from seismic data, there are unknowns, and so on. So tweaking one component of errors, like the parameters, may improve the match, but may also come at the cost of overfitting, where parameters are changed to overcompensate for shortcomings in other model errors, without actually improving the predictive value. To improve confidence here, what we would like is the optimization or calibration to be extended to include additional data sources, and the more the better. And this optimization framework that we propose allows for the integration of many data sources of different nature. I will now get to the conclusion. Next slide, please. To conclude, we observe, in line with earlier studies, that the plume shape is primarily driven by the topography of the top surface, which we do not control in the optimization. The parameters we are adjusting may indirectly affect plume shape by adjusting the vertical distribution of CO2 in each layer. Further confidence in the model could be obtained by integrating multiple data sources. However, we must be careful not to overfit. Conceptually, the degrees of freedom should be kept low compared to the amount of calibration data we have available. And even so, it is hard to say to which extent parameter adjustments reflect reality and to which extent they are changed to overcompensate for other sources of error. To assess actual predictive power, one might consider calibrating the model to a subset of input data and then test the performance on the remaining input data. This is comparable to the standard training and test data approach that is used in machine learning. But this would be a topic for further study. So by that, I conclude and thank you for your attention.
Thanks for that nice, concise presentation, Odd. And I'd now like Tore to deliver his presentation in this first series of 3. Thank you.
Yes, hello. Good day. Yes, my name is Tor Ingmar Bernardo. I will present NECWI-mod, which is short for Improved Non-Equilibrium Darcy-Buckingham Model for CO2 storage. So it's actually a general modification of this Darcy-Buckingham model that can be applied for unsaturated flow and multi-phase flow. But here we apply to CO2 storage. And improved is more a relative term. What I try to do in this project is to address a particular issue with these classical two-phase flow models that do not perform well in this Sleipner case. So this presentation is actually a little bit more of a specific numerical study. So you can go to the next one. Yeah, so the agenda.
Looks like we have a break in transmission. Tora, can you hear us?
I'll describe motivation, the objectives for this project. I'll show some results of this notification dynamic, and I'll conclude next slide.
Tora, we can't hear you very well.
Next slide. Yep. You can't hear me very well. Okay.
I can. We can now. Please continue.
Okay. Maybe this was a little bit of bad position with the microphone. Yes. Okay. So the typical approach to model CO2 migration is to assume the Darcy-Buckingham flow is the dominant process. So the Darcy-Buckingham formulation or model is a formulation for multi-phase flow in porous media that is expressed by extending Darcy's law for each phase with a relative permeability. So at the GHGT 12, I attended and I listened to a presentation by Andrew Kavanagh, and he basically said that the Darcy flow models do not manage to match this Plume morphology very well, neither quantitatively or qualitatively. And also severely limits their utility for future performance. So that's a little bit of a punch in the gut, I guess, when you're working with these models. So one possible reason for this mismatch is the violation of the local equilibrium. For instance, if you have a grid cell, then maybe not all the pore space is actually used. So next slide, please. So here we have several frames showing the Plume extent for 3 different models. And we see the interpreted Plume extent from seismic for different years in blue. So the 2 models on the left is the UP and V, or the upscaled Corey curves model, and the vertical equilibrium models. And then MGN, which is a percolation capillary flow model. And we can see that this MGN, or the percolation model, provides a better fit, maybe actually overestimates the spread by 2008. But the Darcy flow solutions are almost just blobs around the injection well. So I should note that of course this is from 2013. So these models have been obtained better fits than these. But the issue with the mismatch by the Darcy model is still relevant. So, however, if you give these Darcy model a little bit more time, we can go to the next slide. We can see some time frames extending up to 90 years ahead of time. We can see that when you compare the 2098 solution, for instance, with the 2008 observation, we can see that the match is very good or excellent, but it's a little bit it's 90 years too late. So next slide, please. So what I wanted to do in this project was well, the Darcy-Buckingham law was developed for local equilibrium conditions, which does not always hold. So in this project, I wanted to look at 2 aspects that can address this non-equilibrium and also possibly the transient mismatch in the CO2 migration. So the first aspect was A here was to address the large viscosity ratio between the fluids, which can result in fingering or channeling in a porous media by using this something called active region model, a model by Liu and Bolvarsen from 2005. I'll give a short 20-second introduction to that in the next slide. The second aspect that I wanted to look at, sorry, can you go back to the previous? Yeah, so the second aspect I wanted to look at was the stress dependency in the mechanical properties, and to see how that can affect the pore pressure, but that's not a part of this study. And the focus here is on the first aspect. But the hope was that both the combination of these two aspects would temporarily and spatially improve the match with historical CO2 plume migration. Now, next, please. Yeah, so the active region model, or the active fracture model, is it's a relatively simple model in both in concept, I guess, and also in mathematical expression. But the first thing you need to do is to distinguish the driving phase for this non-equilibrium. It can be the water or it can be the CO2, but in this case it is the CO2 that can cause viscous fingering in the porous media. Second, we need to establish the active region parameter, gamma, which is the only new parameter introduced in this model. It is found to be site-specific and material-dependent, and it can be derived, but it probably needs to be inferred from experiments or some field data. So once this is known, then solving the model is just as usual. You specify some capillary pressure and some relative permeability curves, but now with the modification of instead of using the effective saturation in the capillary pressure and the relative permeability, we now use what we call the active region effective saturation. So there's some equation there showing how they're all related, and basically how they're all also derived from the introduction of one parameter, gamma. So let's also note that this active region model formulation collapses to the classical formulation, or the equilibrium formulation, when gamma becomes 0. So the next slide, please. So here we can see the capillary pressure on the left and the relative permeability on the right. So the black lines are considering equilibrium conditions. So that's the standard, let's say the traditional, or how the capillary pressure curve would look, and the relative permeability curves would look. The blue lines are for a wetting drive, but in this case we're looking at this non-wetting drive by the CO2. So we're looking at the red lines, and what we can see is that with increasing value for this gamma, or this active region parameter, then we see that we have a shift in capillary pressure towards higher values. We see also the change in the relative permeability. We see basically that the relative permeability is increased by increasing this, or by introducing this active region parameter. So this will speed up the flow of both phases, but also CO2, and also reduce the pore pressure, which is two sides of this, or two things that are essential for this history matching. So how does this, so finally I want to show just some results, how this looks in a numerical model related to the saturation of injecting CO2. So you can go to the next slide. So the model that we are considering is a disc-shaped reservoir, which is has a rectangular cross section, so it's a 2D axial symmetric model with properties inspired by Utsira. We have injection at the center point there, about 1 million tons per year. We have an open boundary to the right. We have closed boundaries on the top and bottom. And the model is about 600 meters and with some infinite domains aside to simulate that we have a model that is extending about 100 kilometers in this case. So this is a 2D model. Next slide, we can look at some results from this simulation. So here we see some frames showing the saturation distribution of the injected CO2. We have the saturation of CO2 for different times and for different models. So we have the different times in columns. We're looking at 0.05 years, 0.2 and 0.5 years to the right. We have different gamma parameters in the vertical or in the different rows. So the bottom rows shows the equilibrium model where gamma equals 0. So that is the standard formulation and how the CO2 plume would look if you use the standard formulation for two-phase flow. And then the columns above is for gamma equals 0.1, 0.4, and 0.7. And what we can basically see when we go from top to bottom, when we introduce this gamma parameter, this active region parameter, is that with a higher gamma value, we get a lower saturation of the CO2 plume. And also an effect of that is that we have a bigger spread of the CO2 plume. So if you look at the tip of the plume, you can see that if you look at the columns at different times and you look at the different values, you can see that the tip of the plume is extending further the higher active region parameter that you have. So this is the effect of how the saturation is or how the speed of the injected CO2 is affected by this gamma. Okay, on the next slide. So this is my final conclusion, I guess, on this relatively short numerical study. So this active region model or active fracture model is a promising concept for more accurate Darcy-Buckingham flow when the equilibrium is violated. Sorry, can you go back? We see that the benefits of this model is that it captures some observed processes like fingering effects or incomplete flooding in the reservoir. Another benefit is that this active region or active fracture model is also useful for fractured rock, as not all fractures are active. And it's also a relatively simple modification to existing code to consider this active region concept. The drawback, of course, is that you need more data. In this case, it's the gamma parameter. And the second one, of course, is that you have more non-linearity in effects, which might mean that it's a little bit heavier to solve numerically, particularly for high values of gamma. Okay, that was my final slide. So thank you.
Thank you, Tora. Very good. There are one or two questions here. Question to Sarah and Odd. Could you vary the layer horizontal geometry to achieve a better match?
I guess this is referring to the topography, because the horizontal geometry is essentially constrained by the model. I think my perspective here is, I think, and Odd really described it very well, is that you could do that at the expense of something else, and that's for sure something that we could try. But what will we gain? I think it's one thing to get a match, but then if it's overmatched and over calibrated, you haven't gained the ability to predict. And that's the whole point of history matching, is to gain the ability to predict what will happen where we don't have data. And calibrating the topography is not probably the right thing, the right approach, because that is a very local effect. But what you want to really calibrate are the global, more general parameters that you need to use to help predict what's going to happen when more CO2 comes into that system. But maybe, Odd, you want to?
Well, we have done studies in the past where we have tuned the top surface locally to obtain, and we could actually get a very good match, but then you have a lot of degrees of freedom that you are playing with. So the question is, at which point are you actually improving the predictive power of your model? So definitely you can get a good match by tuning the top surface, but you have to consider yeah, to which extent this is actually useful.
Okay, and
could I add a little point, James?
yes, you could.
About the seismic depth conversion, because there's a lot of uncertainty here. And in the reference model for Sleipner 2019, we tried to be honest about that. So it's a central guess, but obviously you could change the topography to get a match, but then what do you learn from that? So the whole point is to allow the parameters to be open with realistic constraints. So it's an important point.
Okay. We have some other questions, but I think we'll move on now, and there will be plenty of opportunity later on. So if I could ask Tor Harald to take the stage. And thank you.
Yeah, hello.
Hello, yes, we can hear you.
Yeah.
Off you go, thank you.
So my name is Tor Harald Sandve. I'm working at Norse, and I will present some work we have done together with SINTEF, which we can go to the next slide. So in the spirit of the openness of CO2, the CO2 data share, you can go, yeah, there. We want to we have focused to make an open workflow for the whole history matching, where we have used the ERT, Ensemble Reservoir Toolbox, mainly developed at Equinor for the history matching, and the OPM flow simulator for the simulation. So this is a full 3D simulations. So instead of tackling the model by simplified VE model, we instead use computer power and run them on clusters in parallel. And the whole workflow for setup, installation of the whole history matching, including installing ERT and flow, is made available at the given website. So at OPM publication Sleipner, where you can go follow the whole process. So it should be possible to reproduce the whole history matching. So you can go to the next slide. So we also for the model we tried to I guess this is similar to both Odd and what Sarah presented. We tried to model vary the permeability in the sand layer and the shale layers and in the feeders. For the sand and shale, we used the given mean values and with some variability. For the feeders, we used a very large deviation so that they could both act as barrier or a shale layer and as highly permeable chimneys. And it was up to the history matching routines to calibrate this. And we also decided to vary the temperature at the top, and we fixed and the temperature is fixed at the bottom at 41 degrees. Next. So for the objective function, or the data we tried to match, the Plume area. So this is different from the earlier presentation where they used the outlines. So we instead used the areas, and we had also added some noise to the seismic data. And for the data assimilation, we used the ASMDA That's the same as Sarah presented, with 50 ensemble members and 5 iterations. So the main difference between what we did and for instance what Odd and Sarah did was that this is a full 3D model, and we used the area to match instead of the plume outlines. So you can go next slide. And for the simulation model, we use OPM Flow, a dedicated CO2 store option, where all the PVT properties are computed internally as function of pressure, temperature, and salinity based on models presented in the literature. For this study, we don't allow dissolution of CO2 in brine, and yeah, we use the relative permeability and capillary pressure from that was given in the Kavanagh paper in 2013, which was the old Sleipner benchmark. And you can see here just a snapshot of one. I think this is the end of the simulations for one of the ensembles after 5 iterations. So you can see this shows the CO2 saturation, how the CO2 migrates upwards in the chimneys and distributes in the permeable layers. Okay, next. Now we can look at some of the history matching results. So here on the top here, what you see here is the areas. The blue star is the data. So that's the computed based on the seismic data. And what you see is the bar plot showing the spread of the areas for the different ensemble members. It's starting from layer 1, and then it shows how during the 5 iterations we are able to get a closer match on the area. We can see this for most of the layers from 1 to 5. You can also notice that for instance for layer 1, there is these small dots are outliers outside of a 1 standard deviation. So it means that some ensembles are outside of that, and you can see that at most of the ensembles just predicts the flow to go through layer 1 initially, but it's able to, the history matching is able to capture this nicely during the iterations. If you move down and look at the contours, what you see here is that in blue it's the data, so that's based on the seismic and the plume outlines given by the data, and the red one is the contour of the ensemble with the least area, and the cyan is the maximum area, and the purple is the best match. So that's where the area is closest. So you can see for layer 1 we get some okay match. For layer 2 you see some deviations and so on. We can go to the next slide to look at the other layers. So now we move on to the top layers. Again, we can see if you start on the top, on the areas, on the plume areas, we see how the history matching algorithm works. It's able to match it, to match the area. But since we are not matching against the plume outline, we see that there is quite large discrepancy. We can see this especially for layer 6 and layer 9. Yeah, then I think we can move to the next slide. So now we will investigate the parameters we have tried to match. We start by with the permeability in the main feeders, So this shows the log 10 in Minley-Darcy. So we can see here that starting out with a large spread, all from -4 to 4 for the first feeders, meaning like we have the permeability of a shale layer to a full permeability of the sand layer. For most of the layer, the ensemble method is able to narrow down the parameter spread to values around 1 milli-Darcy approximately. There is some deviations between the layers. So these are the main feeders. I think we will go to the next, where we look at the additional feeders. So what we see here is that you can see immediately that we have during the history matching iterations, the spread is not reduced, meaning it's less sensitive to these parameters. But remember that we tried to match the area. I think this would have changed if we have tried to match the contour. We can see, especially, then we get more CO2 in southwest and northeast, which was missing in the contour plots. Next. So now we also look at the permeability in the sand layer and the shale layer. I've just picked layer 5 here, but it's the same story in most of the layers, that there is little variations and it's less sensitive to this. And also in contrast to what Sarah presented, we don't notice, or this result didn't show a very clear sensitivity to the temperature, which it was, at least for me, it was a bit surprising. Yeah, I can mention that maybe that was not too clear in the beginning, that we use the temperature gradient, so we don't simulate the temperature, but we use a constant gradient, but the properties depends on the temperature. Next. So final box plot showing the simulation time. So again, here we can start by, so this is simulations for each ensemble members. We use 8 cores, so we run them in parallel, and then we of course we run many ensembles in parallel as well. So this shows the simulation time for one realization. So it varies between 3 and 5 hours on this machine, and you can see that as the parameter space also goes down, also the simulation time is the spread of the simulation time goes down. Yeah, but you see immediately like the whole ensemble run takes approximately 5 or 6 days, so it's quite time consuming compared to the VE models presented earlier. Next slide, please. So just a short summary. So we presented an open workflow for history matching, and please can check it out and try it out going to the web page, where we have put up everything we have done to make it possible for you to reproduce it. What we see from this study is that it's the main feeder permeability that is most sensitive to the area. And what has also been discussed earlier, that we see that there is a top surface has a huge impact on the plume outlines. So for instance, doing history matching, including the geotools like RMS, could be of interest, and that's already integrated into the ERT framework. So it's if you have license to RMS, it should be easy to test that out. Another obvious thing to try is to do what Sarah and Odd showed, to also look at the contour, or in combination with the area. And also one effect that we didn't include here was the convective dissolution. So we have worked on a simplified upscaling approach for this that we have included in our simulator, but we didn't test the history matching workflow with that, but that should be just to run, so it should be easy to test. We can see how this is just like what you see here is a slice of the Sleipner, where we see how the CO2 dissolves into brine and migrates downwards due to the brine becoming heavier when saturated with CO2. And we are also interested in testing this out with more ensembles and iterations to see if that's could improve the history matching. Next slide. So just final slide is just important acknowledgements, both for Gassnova for financing this particular project, and also we'll thank many of the key collaborators and funders for the OPM flow simulator that we have used, and a particular Syntef for collaborating on this project.
Okay, Tor, thanks very much. And we'll move to our final speaker in this section, Adil. Just a word to all of you listening. If you can't hear or there's a break in transmission, you will be able to listen to this on YouTube. So I hope that you can still all hear. I'm hearing the speakers perfectly well. Drop us a note through chat or questions if you can't hear, but otherwise we will proceed. Thanks, Adil. The floor is yours.
Thank you. My name is Adil Zahid, so I will present a few of my simulation results regarding CO2 dissolution in brine. And in previous presentations, you have seen a lot of efforts in matching the Plume. This is more towards like understanding the dissolution. I have not done put any effort in matching the Plume, but it's a more sensitivity analysis study, you can say. Can you move to the next slide? Yeah, on the right side, you can see 4 different mechanisms widely discussed, explained in the literature: the structure trapping, residual one, and then solubility and mineral. And the focus in this work is the solubility trapping, which is the most important, you can say, the geochemical reaction for CO2 storage in saline aquifer. And that's like, that makes this CO2 storage process like more stabilizing and securing long-term storage. And as I said, the objective is to predict or to estimate how much CO2 is dissolved in the brine using this new Sleipner model, and to run different sensitivities to see how different parameters affect the dissolved phase fractions. And we use this Sleipner model. Can you please move to the next slide? Yeah, I think I don't need to spend time on this. It's been already explained, and many of you can also go to the CO2 DataShare, and you can see all the details, the porosities, permeabilities, the layers, PVT model, and the well details. I think I don't need to spend on this. You can go to this CO2 DataShare, and you can see all the details over there. Can you please move to next one? Yeah, so I have used Eclipse 300 model to simulate CO2 dissolution. Eclipse 300 compositional has different, you can say, options. One is CO2 store module, other is CO2 Sol, which is using for depleted oil reservoirs, and then they have gas watt, which they use for depleted gas reservoirs. But I have used this CO2 store module, just a few lines to understand how this model works. It is a mutual, it has mutual solubility, CO2 dissolving in water, and water is going into CO2. And this model is given by Speicher and Proust based on the fugacity equilibration between water and CO2. And then all the explanations how the water fugacity is calculated by Henry law and CO2 fugacity is by SRK equation of state. And then all the details about how gas density and viscosity is calculated, and also the water density and viscosity is calculated. On the right side, I can see it's very small, but if you see on the left figures, it's 100 and 150 all the way it's increased with the temperature, but they have matched their model with different experimental data, and I mean with at different temperature scales. And I personally also test this CO2 store module not only for Sleipner but for example SMEHE also, and then I make a benchmark with another commercial CO2 simulator like CMG GEM, and I see quite close match in predicting the CO2 solubility. And in another study for another model, I see this CO2 store module predict. I make a benchmark with an open source simulator, pFlowtron, and I see also pFlowtron and CO2 store module predicting almost the same CO2 solubility. So that is the model which I use to simulate the CO2 dissolution in brine. Can you please move to the next one? Yeah. So here are the few results. If you see on the left side, this is CO2 dissolved in water phase in kilogram mole, and this is the injection rate. This is the total CO2 injected, 9 million ton, and this is the average pressure in the reservoir. So in this, what I try to see, as I told that it's like a sensitivity study, I use different injection rate. In one, I increase slowly and then decrease the injection rate. In another one, in the red one, I use a constant injection rate for 10 years. And in the blue one, I use another lower injection rate and for 15 years. And you can see that initially, of course, we can see the injection rates affect that we have lesser dissolution in case of slow injection rate, but ultimately, for example, we stop injection in one case, blue and red and green, we stop at 2007 in 10 years time, and another in 15 years time. But when we stop injection, I continue simulating, and we see that ultimately after like 30-40 years, we see the ultimate dissolution is the same. So injection rate has some impact on CO2 dissolution, but in longer run, in longer prediction, it has almost the same dissolution. Can you move to the next one? Yeah, here I injected two different volumes. Like in red case, I injected 15 million ton, and in another green one, I injected 9 million ton. So this is 10.63% is the percentage of dissolved CO2 from the total injected CO2, and then this is 12.56%. So injection volume has effect on CO2 dissolution, and this like from 10 to let's say 12.6%. This range is like quite inconsistent with the experimental with the lab data published in an SPE paper in 2019, and also it's within the upper bound or upper limit of the gravity data published in 2009, which is 21%. So like I explained that the model CO2 store module, I make benchmark with other simulation tools, have quite close match there, and also the estimation of the dissolve phase is consistent with the lab data, and also it's within the gravity survey estimation, which is in 2009. Can you move to the next one? Yeah, in this, what I tried like to see the effect of vertical to horizontal permeability ratio. Same, it's like CO2 dissolve on the left side, and this is same injection rate, same amount of volume injected, and initially you can see that that lower vertical to horizontal permeability ratio has higher dissolution, and that is because the CO2 moves in, you can say, in horizontal and get a bit larger contact area with the brine, and that is the reason we are getting a higher dissolution rate in case of lower vertical to horizontal permeability ratio. If you move to next. Yeah, in this, what I did, I run it for longer time for till 2055, and here you can see that initially that lower vertical to permeability ratio has higher dissolution, but ultimately afterwards the base case, which is 0.1 vertical to horizontal permeability ratio, that gives higher dissolution, because that gives initially the plume was compact, and then at later stage it has like option to move all the way, and that is the reason we see higher dissolution in case of the base case, which is 0.1 vertical to horizontal permeability ratio. And on the pressure side, you can see like initially when you have lesser CO2 dissolve, you see a bit higher pressure here, but when afterwards when we see higher dissolution, and then the pressure comes down. So clearly this vertical to horizontal permeability ratio that also affect the ultimate CO2 dissolution. Can you move to the next one? Yeah, in this I just make a simple simulation to see the effect of salinity. The base case which has no salinity, and the green one where I have like 2.5 moles per gram. This is molality, or in, you can say in mole fractions, let's say it's like a 5% salt solution. And we can clearly see that salinity decrease, and that's what we were expecting. Salinity decrease CO2 dissolution compared to the base case, which has no salinity. I have run many others also. For example, I tried critical gas saturation, effect of critical gas saturation, irreducible water saturation, some other parameters also, but I didn't include because the time was 10 minutes, and I thought that just to give a bit taste that how different parameters affect the CO2 dissolution. Can you move to the next one? Yeah, it's just a summary that that the CO2 dissolution is a dominant mechanism, and during this injection phase or injection, you can say the interval, we have dissolution from 8 to 12, and in vertical to horizontal, it goes to around 16. So let's say it's from 10 to 16% CO2 dissolved in the brine, and then in longer run, it could go even to what I see in simulations to 34, 36%. And as I explained, we see the effect to vertical to horizontal permeability ratio. Residual gas I have not shown, but I have that also affect brine salinity, also affect, and surely there are some other things which we need to look. For example, we need to look the thermal effects on the dissolution. We need to look the grid refinement effect, because if you see in the closer well region, this is because in mutual solubility model, you will see water is evaporating in near well region, and that could also affect. And then there are some other, for example, to see the effect of heterogeneity, also to see the effect of hysteresis, so to see how all these affect the CO2 dissolution part. One thing which I forget to mention, convection driven dissolution, that is not included in these simulations. It's only diffusion. Convection has not been included in this study. So with this, I will just close. I hope I finish in good time.
Yes, thanks, Adil. Before we switch to Philip Ringrose to bring the whole thing together with some concluding remarks, I do have one question for you, specifically to Adil.
Yeah.
Did you try and compare results of co-store with GEM after 200 to 300 years post-injection? And the comment the questioner raises is they've tried in their benchmarking and get very different results with the amount of CO2 dissolution.
No, I have not tried to run for that longer time. And the reason is anybody who is a reservoir engineer, he knows when we turn on the resolution, and if, for example, the model is big and pressure, for example, also, for example, in SME, I have quite low pressure, that takes a lot of time to run. So I didn't try to run for that long time for benchmarking.
Okay. Thank you very much. And Philip, your assessment of, can you put it all together?
Yeah, right, that's going to be tough. No, I would like to thank the 5 speakers for some really excellent talks and opening our eyes to this problem. And for those listening, the first thing I would say is that you might be disappointed there wasn't a right answer. To put it simply, to understand the multi-layer CO2 distribution at the Sleipner site, even though we have excellent time-lapse seismic data, it's not an easy problem. And so in the chat, there's been a lot of discussion about how could we match the topography of the layers better, which parameter is going to give you the best match. And in a way, that is the question that we're trying to ask here, is there is a lot of uncertainty about the topography. Even if you were able to get a better match of the topography at the top, you have a lot of uncertainty of the layers further down. And then in addition, we know from the time-lapse seismic data that there are what we're calling feeders connecting the CO2 between different layers. So I think the first thing to say is that this is an extremely complicated problem. And the second thing is that the whole point of these studies is to learn about what is important in history matching CO2 plumes and how do we better understand the dynamics. And if I was to summarize what we've heard, I mean, we had Sarah looking at vertical equilibrium approaches and trying to capture the thermal effects as well. And we also saw that there was a significant speed up in simulation time if you simplified the model. But then the question is, what simplification is valid? And then Odd Anderson, he explored some of the issues with the topography and the history matching. Whereas Tore Ingvald, he looked at a more fundamental aspect. He said, well, how can we change the actual Darcy equations to get a better match of this process? So my point would be that what's been interesting about these talks is the diversity of trying to understand this problem. And this is not the end, this is the beginning of the problem. And it would be really great if other modeling groups in other institutes around the world started to look at this problem and say, well, you know, how can we learn from it? And so it's a process. So maybe just to throw a question back to Odd and Sarah at the beginning about what your feelings are about what we could do better to handle this business of the topography of the layers. You know, should we use it as a constraining parameter? Should we try and fix that, or should we allow it to be free? What do you think, Sarah? And Odd. Oops.
Yeah, I got it now. No, we were chatting a little bit. I mean, and I think the question was coming from Patrick Zweigel, your colleague at Equinor, you know, pushing us. Well, if you can't match it, then the topography is wrong. Why bother? And my answer is, why not go actually the other way? And we know what the large scale topography of the Sierra really is, right? And if we're really ambitious of looking for how CO2 will migrate, you know, if we inject it Sleipner for another, I don't know what the plans are, 10, 20 years, you know, it's going to be well beyond where it is now. And what really should be thinking about are the large scale features and matching those and matching volumes and matching vertical distribution due to these intermediate layers. And forget about this, not forget about the fine scale, but just use that as a slightly, you know, small tuning parameter and not try and capture these very precise outlines. It's really missing the forest for the trees approach.
Right.
So I think that's one way of doing it. But you know, that's so that would be my thoughts there.
That's a good point. Odd, any reflections from you?
I also think that it's interesting to try to modify the global features of the top surface in order to see if that can improve the match, such as not just tweaking local points of the surface, but more global effects such as tilt or low frequency geometric features. Also, it could be interesting to not, I mean, plume shapes is one way of matching to data, but there are other data sets that we could include in this objective function that we're trying to optimize for. We are currently looking into gravimetric data in a similar project on the same model. And we also hope to integrate other sources of information that goes beyond just looking at the top surface.
Yeah. I mean, in the chat, Petter Zweigel made the point that maybe we should match to mass per layer rather than the details of the shape. And I think that's a very good point, is that, you know, we do know the distribution of CO2 per layer relatively. So that's probably quite an important constraining parameter. And the actual details of the shape may not be that important. But I think the other thing that's been revealed in the last two talks, we're talking about, well, should you include dissolution or should you neglect thermal effects? And we know that those effects do occur. There are thermal effects and there are dissolution effects. So then the other challenge is, what do we do to get those effects in as well as the shape of the mobile plume? And I think that's a topic that we're actually quite immature on. You know, there's still a lot of work to go on understanding thermal effects and the dissolution between brine and the free phase. I don't know if Tor Harald or Tor Ingrid would like to say anything about why they approached the problem the way they did. Tor Harald, because you got some large scale.
I can make a. Yeah, I mean, I can comment on the 3D part, or I can start commenting on the dissolution, because I've been working on that for some time now, including the convective dissolution, and as I said, I have not done that in the history matching loop, but I will really like, that's something on my agenda that I will try.
Is that a next step in your view?
Yeah, I think so. I mean, at least simulations I have done until now confirm what I mean. Also, Adil sees that the effect of convective mixing is important, and I think that's also an important history matching parameters that can be that should be included.
Yeah, you kind of showed a global history match, Tor Harald, with a full simulator and multiple parameters. And again, you got a kind of crude match per layer, but then there's further work to be done, right?
Yeah, I mean, I didn't try to match the plume outline at all, but only the area or the volumes. Yeah.
Tore, is your approach to the Darcy equations, is that neglecting dissolution at this stage? You're just looking at the relative permeability effect, correct?
Yes, the model that I used at least does that. But just to answer the first question, you have why did I look at this? And I think it was basically because I really identified with what I saw in that presentation a long time ago by
Kavanaugh. Oh, your line has frozen again, Tore.
I think he was going to say Kavanaugh.
He was going to say Andrew Kavanaugh's presentation.
So I was curious how that can be proven across this theory.
Tore, you're going to have to repeat
so
what you said. Your line is.
You missed my whole
again.
brilliant speech there.
Yeah. Can you say it again briefly, Tore? Because now we hear you.
I see that my camera is actually down, but yeah, okay, yes, no, I could. Yeah, what I was saying is that I could really identify to what was presented to me in that that presentation at the GHGT in 2013 by Kavanaugh. So I saw the same thing. So I wanted to look into why is that? Why does my results look like that, and not being able to kind of reproduce this this migrational patterns that we see. And then I came across this theory about this active region model, and I thought it made sense, and I could see that it was validated in many different examples. So so I tried to apply it to my two-phase flow simulation.
Yeah, very good. And you know, I think I would just like to maybe connect to others in the audience here that, you know, the objective here is not just to match Sleipner. The objective is to understand these processes, and we see that the simulators are evolving all the time. We've had the vertical equilibrium approach very much addressed over the last years, but also the thermal effects. And now Adil is, you know, trying to get an understanding of the dissolution effects. So I would say the bigger challenge that we have here is to use the Sleipner dataset to understand the flow processes. That's the ultimate goal of this work. And it could be that in a year's time or something like that, we have a fuller session, like at a conference, to try and explore this further. Any other inputs from the speakers, or are there other questions that we've heard from the audience that we should take? James, are there any more questions from the audience we should take?
Just a minute, where have we gone? We do have some more questions. There's a specific one for Tura. It says, in the non-equilibrium, the gamma calibration requires data. What kind of data is needed to tune the gamma parameter?
Yeah, you would need some experiments or some field data where you can say something about this active region, let's say active region fraction that you have. So you have a porous media or something, and then if you can back calculate what this active or this f parameter would or f this fraction would be, then you can derive this gamma value. So I would say maybe lab experiments or field experiments where you can say something about the saturation.
And then there's a general question here. It says, where do the measured Plume outlines come from, and how have they got resolution down to 1 meter thickness?
Right, I saw that question. So I could briefly say that, yeah, the outlines come from interpreting the time-lapse seismic amplitude maps. And the best resolution is down to 1 meter on the top layer, the layer 9. But as you go deeper, the resolution is much poorer. So there's always an amount of the plume that you do not see with the seismic data. So it's also important for the modelers to appreciate that the outline of the plume from time-lapse seismic is only also an indicator of where most of the CO2 is, not where all the CO2 is.
Yeah.
And you know, and that's another part of the complexity of this problem. So it's a good question.
So I think, as you rightly say, Philip, this is really an exercise in trying to understand these processes. Now, I might be a little bit general here, but it's fair to say that Sleipner is very well studied and understood. After all, you've had what, 25 years injection, something like that?
This year it's the 25th anniversary, yes.
Right, and it is quite a shallow reservoir by comparison with some. I mean, okay, so it means that you can get relatively good resolution. But it does beg the question, if we're trying to understand these processes elsewhere, doesn't that mean that potentially new sites and even existing ones where injection is still going ahead fairly successfully, that a lot more data and analysis is going to be needed? And where I'm going to with this is, it sounds like the modeling processes, we need to sort of compare the modeling processes that you've understood in Sleipner and how well that's going in other big sites.
Yeah, I think I can see where you're going, James, and I think you're right in the sense of a deeper site will have hotter CO2 with a different density. And for example, in Canada, you have the Equinor project injecting at 3 kilometers depth, but they have time-lapse seismic data So there's no reason why you couldn't apply the same models we're applying at Sleipner to a much deeper site with hotter properties. So I would say the methods we're developing are applicable over a wide range of depths. But I do agree with you, James, it would be nice to have more calibration data from more sites, certainly. Is that what you were thinking, Sarah?
Yes. Well, sorry.
But certainly more calibration data or more case studies would be welcome. But
Yes,
I wouldn't like you to think that this is not valid for elsewhere.
No.
Yeah, I was going to say two things. Gravity is the same everywhere. So
Yes.
buoyancy will always be a factor and topography will always be a factor. I think that we know now. Temperature is very particular for Sleipner, and you mentioned shallow, and not just from the seismic perspective, but from the critical point of CO2. It's very near and sometimes under the critical point with respect to the temperature and pressure. So that may be unique for Sleipner, the sensitivity to temperature that some of us see and some of us don't. So that, yeah, but you know, there'll be new things that come, and I think that's what Philip said. We need calibrated things to calibrate and to see what are the new things that pop up and different, so that we have models that are more robust in the long run.
Good.
Agreed.
Right.
So
Well,
should we wrap up, James?
Yes, I think we should. First of all, I'd like to thank Sarah, Odd, Tor, Adil, and Philip for all your constructive and detailed contributions. I would say I think we've got the basis here for building up comparative and case studies. As many of you know, many of the listeners know, we do operate one of our networks is a modeling network. And I think we have the basis for quite a good session. Could well be online, a bit like this, who knows? But anyway, thank you all very much indeed. Just a reminder to our listeners that this webinar will be available on YouTube, and those questions we may not have been able to answer today, we will circulate to the team and come back to you with some answers. So thank you once again.
Thank you and goodbye.
Thank you.
Thank you.
Bye-bye.
Bye-bye.
Bye.
Bye, everyone.
Thanks.